In Chapter 3, Section 4, we have 3 final theorems to go over. This is our absolute putting it all together. Now you can factor whatever you want to factor and graph kind of section. So we will be using everything that we have learned until this point, and we will figure out how to start. We know how to find factors of polynomial functions using synthetic division, but we've always been given a starting place up to this point. We've been told this value is a root. What if we don't have a starting place? How do we know where to start? What numbers do we try? Because there's literally an infinite number of possibilities. So we have to have something to narrow that down. Our rational zero theorem is how we narrow that down. Our rational zero theorem is going to give us a list of possibilities P over Q. It gives us a list of possibilities, things to try, and that list is in the form of P over Q. Now, let's read the theorem and interpret what it says. As always, you're not going to have to reproduce the theorem, you just have to be able to use the concept behind it. So if I have a polynomial function f of x, and it has some first term, say nth degree with its coefficient, and it counts its way down with every term represented until I get down here to the constant. This function has integer coefficients. Now that part is important. Integer means my positive, negative whole numbers and zero. And P over Q, where P over Q is reduced to lowest terms, is a rational zero of the function. Then P is a factor of the constant, and Q is a factor of the leading coefficient. So these are the key statements. P is a factor of the constant right here, and Q is a factor of the leading coefficient right there. We get this list of possible rational zeros P over Q. Now, every value in the list is not a zero of our function. But if there is a rational zero for the function, it will be in the list. My function could have zeros that are irrational or imaginary. They're not going to show up in the list. But if there is a rational zero for my function, if a rational zero exists, it is in the list. So not every value in the list will work, but if a rational zero exists, it is in the list. All right, for example, we have some examples to come up with our list of possibilities P over Q. We're going to find the possible rational zeros for each of these 3 functions. My first function, f of x, equals 6x squared minus x minus 35. I'm only interested in the constant and the leading coefficient. The constant is where I find my values for P, the numerator, and the leading coefficient is where I find my values for Q, the denominator. I need to look at the factors for these values. My factors for P, my factors for 35. Well, 35 is either 1 times 35 or 5 times 7. Notice how I think about pairing those up. 1 and 35 or 5 times 7, I meet in the middle. Those are my possible values in the numerator, P. Now, to get the possible values for the denominator, Q, we look at the leading coefficient, which in this case is 6. Well, what are my factors of 6? I have 1 times 6 or 2 times 3. So those are my factors of 6. Those are the possible values for my denominator. Now notice I didn't talk about positives or negatives because every value in the list we consider both positive and negative. So that when I create my list of possibilities P over Q, I say, okay, all of the positive or negative possibilities, and then I open my set of parentheses. I'm going to start with a denominator of 1 because that's my first factor of 6. And I'm going to put all of these values for P over 1. So that would be 1 over 1, 5 over 1, 7 over 1, and 35 over 1. Well, anything over 1 just reduces to the whole number, right? So in essence, we're starting with 1, 5, 7, and 35. Then I'm going to take each of these factors and I'm going to put them over 2 because that's the next factor. So I have 1 over 2, 5 over 2, 7 over 2, and 35 over 2. None of those are going to reduce. Then I put each of these numbers in the numerator over 3 because that's the next factor in my denominator. So 1 over 3, 5 over 3, 7 over 3, 7 over 3, and 35 over 3. And finally, I go back through one more time and I put them all over 6. So 1 over 6, 5 over 6, 7 over 6, and 35 over 6. That's a long list. Now, I'm not going to rewrite my list. These are the same as just my whole numbers there. I could rewritten that just as 1, 5, 7, and 35. None of these reduce. None of these are repetitions. So this is a big, long list. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 positive values and 16 negative values in my list of things to try. Now, if I'm trying things to solve this, I'm not going to start with all these fractions. I'm going to start with these whole numbers, positive and negative first. I'm going to make it easy on myself. But typically, your list is not going to be that long. It's not going to be that ugly. And we wouldn't need the list anyway, because this is quadratic. We would start by just factoring. Let's look at g of x and see what we get there. Now, we are using the same location for our possibilities. 6 gives me my factors for p. What's the coefficient of my leading term? Well, it's just 1. So q is 1, which means I don't have any fractions. I just have whole numbers. And we already identified our factors of 6 as 1, 2, 3, and 6. So this list of possibilities, p over q, is a lot shorter. We've still got plus or minus. We've got 1 over 1, 2 over 1, 3 over 1, and 6 over 1, and that's it. So we have 4 negative possibilities and 4 positive possibilities, and we would try these using synthetic division until we found our rational zero. In my math lab, be cautious because a lot of these problems are multiple choice and they'll mess with you. They will put values that don't belong, like these values all belong in the numerator, not the denominator. So they'll throw you a value that shows up, but it's in the wrong spot. So just pay close attention. Let's do one more. H of x. Our values for p come from the denominator, from the constant. They go in the numerator, they come from the constant, sorry. 3 is prime, so the only possibilities here are 1 and 3 for my numerator. The values for q, my denominator, come from the leading coefficient. 4 is not prime. I have 1 times 4 or 2 times 2, so I have 3 different factors of 4. When I create my list of possibilities that I would try using synthetic division to find a rational zero for this function, I put 1 and 3 over 1, so those are my whole numbers. Then I put 1 and 3 over 2, so 1 half, 3 halves. And then I put 1 and 3 over 4, 1 fourth, 3 fourths. None of those is repeated, none of those reduces, so that's my list. I have 1, 2, 3, 4, 5, 6 positive values I could try and 6 negative values I could try. Once again, a reminder, not every root of a polynomial function is rational. Some are irrational or imaginary, and those 2 types of roots are not going to show up in my list. All right, next theorem, the conjugate pairs theorem. If p of x equals 0 is a polynomial function with real coefficients and the complex number a plus bi is a root, then a minus bi is also a root. What this tells us is that complex roots come in pairs, conjugate pairs. One is positive, one is negative. And this happens because of our quadratic formula. If you think about how our quadratic formula, where we derive those roots, is structured, if this radical doesn't go away, Then I have negative b plus this value, and I have negative b minus this value. So if this value is irrational or imaginary, I'm going to have two complex conjugate roots. For example, if one root is 2 plus 3i, I automatically know that I have a root 2 minus 3i. If I have a root that is negative 6i, then I also have the root positive 6i, because imaginary roots come in conjugate pairs every single time. Let's put some of this to use. For this first example, it says to factor this polynomial function f of x completely. Well, it's a third degree polynomial, so we know we can expect 3 roots total. They may not all be 3 different roots. We don't know how to just straight out factor a third degree polynomial. So we're going to have to find that first root using synthetic division. Then we will have a quadratic, and we can try to factor that quadratic equation, or quadratic expression, excuse me. Since we don't have a starting place given to us, we have to use our values, our list of possibilities, P over Q, rational zero theorem, to find a starting place. List of possibilities P over Q. P comes from the constant, Q comes from my leading coefficient. Well, 1 is prime, so we have a very short list. We have 1 over 1 or 2 over 1. So we have 2 positive possibilities and 2 negative possibilities. Trial and error here. There's only, at worst, if we don't do well, we will have to do 4 different synthetic division problems to find our rational zero. So let's just start somewhere. Let's start with a positive 1. If I do synthetic division with a positive 1, and I've got every term represented here, I would have 1, 1, negative 5, negative 2, and I'm looking for that remainder, hoping it will be 0. With synthetic division, I always bring down my first term, multiply on the outside, add on the inside, multiply on the outside. Oh, look there, this isn't going to work. When I add on the inside, I get a negative 3. That is not going to add to 0 over here, right? That's not going to add to 0. So positive 1 is not a root. So let's try negative 1, see if it works. I go back to my setup to see if I do any better with a negative 1. Bring down my first number, multiply on the outside, add on the inside, multiply on the oh yeah, no, that's even worse, right? That does not add to 0, so that one doesn't work either. Well, we tried positive 1 and negative 1. Let's try positive 2. So we go back to our coefficients, and we're checking for that remainder. Here we go, bring down the first term, multiply on the outside, add on the inside, multiply on the outside. Oh, this looks promising. Add on the inside, I get a positive 1, multiply positive 2, there's my 0. That works. So we have found our root. So this factor would be x minus 2. And this quotient gives me x squared plus 3x plus 1. Okay, we need to finish factoring because we're told to factor it completely, which means I need to factor this quadratic. But when I'm looking at this, that's not factorable. Since this is not factorable, I'm going to need to use my quadratic formula or completing the square, but I usually use quadratic formula. And since I'm going to have to use the quadratic formula, because this is not factorable, that means that this is my only rational root. Negative 2 wouldn't work. X plus 2 is not a factor. This is my only rational root. So I take my quadratic that is left, and I use my quadratic formula since it's not factorable. I know that the other 2 roots, third degree, I expect 3 roots because of my n-root theorem. I know the other 2 roots are going to be either imaginary, conjugate pairs, or irrational, conjugate pairs. x equals negative b, so that is a negative 3 plus or minus square root of b squared minus 4 times a times c, all over 2a. And I need to simplify. So I have negative 3 plus or minus square root of, well, 3 squared is 9. 9 minus 4 is 5, all over 2. You know what? Square root 5 does not simplify. So my two irrational roots are going to be negative 3 plus square root 5 over 2, negative 3 minus square root 5 over 2. So these are my two irrational roots. They'll show up on my graph. They're just not nice integers. Then this is my rational root. It's my rational root. So there's my solution set. Two irrational roots, one rational root. My rational root was in my list of possibilities, P over Q. That's what I started with. I only had to find one root using synthetic division because it was a third-degree polynomial. All three of these will show up on my graph. I would just have to plug this into my calculator to find an approximation to graph it. All right, the next question it asks us to do is to find the polynomial function with the root negative 4. So this time I'm working backwards. I have a root and I need to find the function. Well, negative 4 is imaginary. And because of our conjugate pairs formula, we know that imaginary roots come in conjugate pairs. So I also have the root positive 4i. So I have two roots. I have x equals negative 4i and I have x equals positive 4i, and I'm working backwards to create the polynomial function. The first thing is to move that over to turn my root into an expression. So this expression would be x plus 4i, and this expression would be x minus 4i, and that's going to give me my polynomial function f of x when I FOIL those together. Now, when I FOIL together imaginary roots, complex imaginary roots, some interesting things happen. Let's work through that FOIL process. X times x is x squared. My outside product is a negative 4ix. My inside product is a positive 4ix. And my last product is a negative 16i squared. 4 times negative 4 is negative 16. I times I is I squared. Now let's see what happens. My outside and inside product is going to add to 0 every single time when I'm multiplying conjugates. That is going to add to 0. I squared, we never leave I squared. Think about this. Square root of negative 1 is I. If I square both of those, my pen is skipping on me, I get I squared is equal to square root squared leaves me with negative 1. So I always replace I squared with negative 1. Now I've kind of run out of space here, so we're going to move over. Since these two terms add to 0, I've got f of x is equal to x squared. This is just 0. This is negative 16. I replace that with negative 1. Negative 16 times negative 1 is plus 16. Anytime I start with just two imaginary roots, those conjugate pairs, I'm going to end up with the sum of squares. Sum of squares is not factorable. Difference of squares is, but not sum of squares. Let's do another one of these where we are finding the polynomial function given a set of roots. This time I'm given 3 roots, 5, 3, and 2i. This is an imaginary root, so it has a conjugate negative 2i. That means I have 4 roots, which means I have 4 factors. So if I'm finding the polynomial function, let's call it g of x, I need to turn each of these roots into factors. That's going to change the sign on each of those. So if x equals 5, then I have x minus 5. If x is equal to 3, that gives me x minus 3. And then I have those imaginary roots. X minus 2i becomes that factor, and then x plus 2i is my last factor. I'm going to FOIL these, pairing up my conjugates. Every time, make sure you pair up your conjugates. For this first FOIL, x minus 5 times x minus 3, I get x squared minus 3x minus 5x plus 15. My middle terms, outside and inside products, are like terms, so I can combine them. So this simplifies to x squared minus 8x plus 15. Now let's look at our imaginary roots and FOIL those. X times x is x squared. Remember that my outside and inside products are always going to add to 0, so I'm not even going to write that down. Then I have negative 4i squared, and my I squared is negative 1. So this is x squared plus 4. Now I need to multiply together this trinomial times this binomial. You need to make sure you multiply each term times every other term. You can just straight out do that if you're comfortable with it. If you have a little trouble with that organization, I suggest using a chart. So we have a trinomial times a binomial. So I'm going to set up a 2 by 3 chart. My binomial is going to go here, x squared and 4. My trinomial is going to go across the top, x squared, negative 8x, 15. Just like you would fill in your multiplication table chart when you were in elementary school, we're going to multiply through. So for the first row, we multiply x squared times each of these terms. X squared times x squared is x to the 4th. X squared times negative 8x is negative 8x cubed. And x squared times 15 is 15x squared. Then I move to the second row and I multiply 4 times those 3 terms so that I have 4x squared, negative 32x, and 60. Now I'm going to combine like terms and list them in order with my largest exponent first. So g of x is, well, x to the 4th is my largest exponent. Then I have negative 8x cubed. I have 2 squared terms to combine, so that's plus 19x squared. Then I have minus 32x and plus 60. So there's my polynomial function that we created from the given roots. Okay, let's look at some practice problems. Now we have a lot of practice problems here. We are going to focus on the evens. We're going to skip the odds and focus on the evens so that we have some practice, but our video is not horribly long. Number 2 is a 3rd degree polynomial. We have our leading term given to us. I see that my leading term is x cubed right there. Positive coefficient, odd exponent, so my end behavior is going to be that it starts low, finishes high. It is not factored, so I'm going to have to do some work to get it factored. I can, however, look at it and know my y-intercept, because if I plug in 0, these terms all go to 0, and I'm left with negative 4. That's a point that's definitely going to be on my graph. 1, 2, 3, 4, 0, negative 4 is my y-intercept. I do need to factor it, and since I don't have a starting place, I'm going to use my rational zero theorem to come up with possible rational zeros based on the constant and the leading coefficient. So my possible rational zeros, p over q, are going to be the positive and negative values. Well, my factors of 4 are 1, 2, and 4, and then my coefficient is just 1. So I only have 3 positive factors and 3 positive zeros and 3 negative zeros to try. Let's pick one to try. It's possible that more than one will work. We just won't know till we try. Let's start with 1. If we do synthetic division with 1, our coefficients are 1, 1, negative 1, or negative 4, and negative 4. We don't need to use a 0 placeholder because we have all terms represented. So let's try this out. We bring down that 1, and we have 1 times 1, add in the inside, 2 times 1, and we get a negative 2. That's not going to work. That negative 2, that does not add to 0. So positive 1 does not work. Let's try negative 1. So again, my coefficients are the same. Bring down the 1. When I multiply on the outside, this time I get a negative 1. That adds to 0. And anything times 0 is 0. So that gives me an, oh, that works. There we go. It gives me a negative 4. Negative 1 times negative 4 is positive 4. That adds to 0. So that one worked for us. So we've got negative 1 is a 0. This factor would be x plus 1. And then I use this quotient, and it gives me, I factored out 1 degree, so this 1 is going to be the coefficient of a squared term. So I have x squared plus 0x minus 4, which is difference of squares. Difference of squares factors out to give me conjugate pairs. So my factored form would be x plus 1, x plus 2, x minus 2. My zeros, therefore, are that negative 1 that we found over here, and then negative 2 and positive 2. The multiplicity of each of those zeros is just 1 because that's the exponent on each factor. Since those multiplicities are odd, the behavior at each x-intercept, at each root, is to cross the x-axis. They're not going to flatten out because it's just multiplicity 1. So I'm going to cross the x-axis at negative 1, at negative 2, and at positive 2. And then I've got this y-intercept to hit down here using my end behavior, telling me I start low, I cross, 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 finish high. That is the general shape of this graph. Let's do one more on number 4. As I said, we're just going to do the even examples. We're going to skip the odds for now. Number 4. We have the function f of x with a leading term of negative 2x cubed. Still odd exponent, so still one end up, one end down, but this time we have a negative coefficient. So overall, it is a decreasing function. So I'm starting high and I'm finishing low. It's not factored yet. My y-intercept, if I plug in 0 for x, would be negative 6. So I can go ahead and think about getting that on my graph. And I need to figure out how to factor it. It's a cubed function, third degree, so I need to find one root using synthetic division. I need my possible rational zeros, list of possibilities p over q. That's going to be my positive and negative options. P comes from the constant, Q comes from my leading coefficient. This time Q is 2, so I have 1 or 2. P is 6, so I have 1, 2, 3, and 6. I have more possibilities this time. I'm going to have 1 over 1, 2 over 1, 3 over 1, and 6 over 1. And then I go back and I put each of these values over 2. Well, 1 over 2 is 1/2. 2 over 2 is just 1. It's already on my list. 3 over 2 is 3/2. 6 over 2 is 3, and it's already on my list. So there's my list of possibilities, positive and negative. And I'm going to tell you that all 3 of my zeros are rational zeros. They are all values on this list. For the sake of time, we're going to go ahead and pick one that I know works. If you're doing this on your own, you're just going to have to use trial and error till you find one that works. I'm going to give you a hint and tell you that negative 2 is one of my rational zeros. So I have every term represented. I set up my synthetic division, knowing that that should give me a 0. Here is my remainder. Bring down my first term, multiply on the outside, add on the inside. And sure enough, that gives me my 0. So this first rational zero is a negative 2. that is the same thing as the factor. That would be x plus 2 in factored form, right there. And then my quotient is interpreted as negative 2x squared plus 7x minus 3. Now, I don't like to factor things with negative squared terms. So the first thing that I'm going to do there is to pull out a negative out of this trinomial so that this squared term is positive and I can successfully factor it. So I'm going to pull a negative all the way out front, and I'm going to pull it from this trinomial. So it's going to change these signs to 2x squared minus 7x plus 3. Now I can factor this quadratic, and it is factorable. In my factored form, I have a negative 1 times x plus 2 times, and then my two factors from this trinomial are going to be 2x and x, both negatives here. I want to end up with 7. 3 is prime. If I multiply 2 times 3 here, I get 6x, and then that gives me 1x for my 7x. This is factored form. We already know that we get negative 2 from this factor. This factor, if I set it equal to 0, gives me a positive 1/2. And this factor, if I set it equal to 0, gives me a positive 3. Those are my roots. Multiplicity on each is 1 because that's the exponent for each factor. So the behavior, since that multiplicity is odd, is that the graph will cross at each of those roots. I have negative 2, positive 1/2, and positive 3. Going to cross at every place. My end behavior tells me to start high, finish low. Oh, I should have gone down further. That shouldn't be my turning point. So if I'd paid closer attention, this would have dipped further and come back up, and that would not be there. Doesn't really matter. What matters is that I've got going up this way, down this way. I've got a relative minimum here, a relative maximum there. Okay, let's look at number 6. I hope you are all remembering that you can pause at any time and slow me down. That way, repeat things as you need it. Here in number 6, we are creating the polynomial function again, depending on working from our given roots. This time we've added a step in that we have to check to make sure our coefficients are correct. So let's create the function g of x with the given roots, and then check our value at the end. N equals 4 means that's the degree we should end up with. We're given 2 imaginary roots. Because they're imaginary, we know they have conjugate pairs. So we know if we have positive 3i, we also have negative 3i. If we have positive I, we also have negative I as a root. That means when I set up my function to multiply things together, I need to set up 4 different factors. So I have x minus 3i, x plus 3i, x minus I, x plus I as my 4 factors. When I FOIL these, I choose to FOIL the conjugate pairs because that keeps things simple. When I FOIL the first 2 together, I get x squared, outside and inside products add to 0 because they're conjugates, minus 9i squared. That I squared is the same thing as negative 1, so that is x squared plus 9. For the next set of conjugates, I have x squared, opposite or outside and inside add to 0, minus I squared. I squared is negative 1, so that is x squared plus 1. Now I FOIL together those those 2 binomials. So the proposed g of x that I get is x squared times x squared is x to the 4th. There's my n equals 4, 4th degree. X squared times 1 is 1x squared plus 9x squared is 10x squared. And then 9 times 1 is 9. So that's my proposed polynomial function. But I'm not done. I was also told to make sure that if I plug in -1, I get out 60. So let's plug in -1 and see what we get. Well, -1 to the 4th plus 10 times -1 squared plus 9. -1 to the 4th, all those negatives pair up, and that's just 1. -1 squared is just 1 times 10 is 10, and then I have plus 9. So if I plug in -1 to this given proposed function, I just get 20, not 60. Well, let's see what we would have to do. If I multiply 20 times 3, I get 60. So I'm going to take this factor of 3 and multiply it in to everything in my proposed function, which gives me a g of x equal to 3x to the 4th plus 30x squared plus 27. This time, if I check it again by plugging in -1, I get 3 plus 30 plus 27, which is equal to 60. So that is how I do that final check where I'm given an additional value to go by. All right. We have a challenge problem and then Descartes' rule of signs. My challenge problem is really not challenging as far as the problem itself. It's just how we set up and deal with this 1 minus I complex root. If I have 1 minus I also have 1 plus I because those imaginary roots come in conjugate pairs. We're going to set this up. This gives me 3 roots. My first root, the real root, is 2, so that gives me the factor x minus 2. And then here's where my notation is a little interesting. This is the challengey part of this. Now you're going to see, I think, one of these on the homework. I don't think I give you any complex imaginary roots on the exam, but I do want you to be aware of it. So my first root would be x minus 1 minus I. And then my second root is going to be x minus 1 plus I. Now for right now, I'm just not going to worry about this x minus 2, and I'm going to work with these 2 roots. I'm going to do some rearranging. First, I'm going to distribute this negative inside for both of these. So this first one would give me x minus 1 plus I. And the second one would give me x minus 1 minus I. Now I'm going to regroup so that my x minus 1 is what's in parentheses for both of those. And now I'm going to FOIL. When I FOIL these two together, x minus 1 times itself is x minus 1 quantity squared. My outside product and my inside product are going to add to 0 because these are conjugates. And then I have I times negative I, which is negative I squared. Whoops, sorry. So I have to do 2 things. I have to FOIL this, and then I have to change this. I squared is -1 times a negative is plus 1. When I FOIL this, it's the same as x minus 1 times x minus 1. My shortcut is x squared minus 1x times 2 is a negative 2x, and then -1 times -1 is positive 1. So when I combine that like term, that gives me x squared minus 2x plus 2. And don't forget that we had this factor, so I need to bring it down, and I need to multiply that times x minus 2. I can do this by straight up distributing everything to everything else, or I could set up the grid like I did in that other example. I'm going to stop there and let you finish that on your own, and we're going to talk about Descartes' rule of signs. Descartes' rule of signs gives us a way to narrow down the possibilities. If my list of possibilities P over Q is really long, Descartes gives me a possibility to say, you know, okay, should I start with the positive options or should I start with the negative options, so that I don't have quite as much trial and error to do. With Descartes' rule of sign, we identify variation of sign as the place where the sign of consecutive terms changes. it tells me that the number of positive real roots is going to be equal to the number of variations of sign in p of x, or less that by an even number. The number of negative real roots is going to be equal to the number of variations of sign in p of negative x, or less that by an even number. Let's do one. Here's p of x. How many variations of sign do I have? We're checking for the number of positive real roots. Well, this sign is positive, this sign is negative, so that is one variation. Stays negative, changes to positive, that's another variation, changes to negative. So we have 1, 2, 3 variations of sign. So that tells us to expect 3 or 1, because of that less that by an even number, so I subtract 2, 3 or 1 positive real roots. Those positive real roots could be rational or irrational, but they won't be imaginary. If they're rational, they show up in my list of possibilities p over q. Then I have the number of negative real roots. I check it by checking p of negative x. So anywhere I have an x, I plug in a negative x. Well, let's see what happens. When I have an odd exponent, it's going to change the sign on that term. When I have an even exponent, the sign on the term doesn't do anything. Odd exponent changes the sign on that term. Even exponent stays like it was. Odd exponent changes the sign, and a constant is constant. So this is p of negative x. Now I look for variations of sign. Negative term, changes to positive. Changes from positive to negative, stays negative, stays negative. So I only had 2 variations of sign this time. Well, 2 minus 2 is 0. So I have 2 or 0 negative real roots. Faced with these 2 options, should I try, when I look at my list of p over q, should I try the positive values or the negative values? Well, I should try the positive values. I should try the positive values for p over q, because I'm guaranteed at least 1 positive real root, and I might have 3 in that list. Now I could have up to 2, I could have 2 negative real roots, but there might not be any. Since this is not a sure thing, when I look at my list of possibilities p over q, I'm going to start with those positive values, not the negative values. Our last note says, the number of roots predicted includes both rational and irrational real roots. Remember that part. That means that those irrational roots do not show up in our list of possibilities p over q. For example, the roots of this function are irrational. They won't be in my list. So if I tried to use my list of possibilities p over q to help me factor this, it would not work. Now, I'm not going to give you a function that does not have at least 1 real rational root, because I'm not going to set you up to fail. But just know, be aware that is a possibility.